Kevin Stelzer. I'm going to read this bio and then I'll make another couple of comments. Kevin Stelzer is a principal of B&H Architects, and he focuses on laboratory, healthcare, and educational building types across Canada, the United States, the UAE, and Asia. He studied architecture at the University of Waterloo and studied building science at the University of Toronto. He's a licensed architect, a building science specialist of Ontario, and a LEED accredited professional. He serves on the CAGBC Energy and Engineering Technical Advisory Group and on the United Nations Sustainable Buildings and Climate Initiative Task Force. He has extensive experience in sustainable design, construction documentation, and engineering coordination. He has participated in some of Canada's most compelling sustainable projects, including the UBC Student Union Building with B&H in Dialogue, the Centre for Engineering Innovation at the University of Windsor with B&H, the Integrated Learning Centre at Queen's University with B&H, the TDCCBR, one of the most extraordinary buildings at U of T with Architects Alliance and Benish, and the York University's Computer Science Building with Architects in Busby. And he's an amateur naval architect. He lives with his wife and 2 daughters in Toronto and walks to work. I first got to know Kevin as one of the most brilliant students I'd ever met. And he has perhaps, I have to say something personal about it, because he's offered 3 kind of key ideas that have had a great influence on me. The first was in his thesis in which he was conceiving of computational design in terms of projection and arraying, and took the idea of cellular accretion to a kind of a visionary point at a time when there was very little evidence or even language to think about computational design. He then went on to help me launch my practice as one of my very, very first associates, and helped conceive of digital practice per se, making a bridge as one of the very first people who took on digital media in the school, between manual drawing and philosophy and thinking and automated projection. Perhaps more recently, he gave a presentation, I think it was about 3 years ago, which I think serves as a fundamental kind of mark in the school in the conception of subtle phenomena, material precisely addressed subtle phenomena, thermal loops around a body, the action of air and of pressure differentials around building envelopes, and offered as a gift to the school a series of building sections in exploring just how ductless buildings and buildings conceived for thermodynamics might be orchestrated in an absolutely direct and meticulously rendered way. This is a very special person, and it's wonderful that he's here. Thank you, Kevin.
Philip, I'm embarrassed and really in touch with that introduction. Thank you very much. Thank you very much for the invitation. And I love these sort of symposia events. I do feel that, as Philip mentions, they offer a real direct engagement with a lot of sort of techniques that can help us collectively as practitioners develop some of the dreams and ideas and concepts that really drive our imagination. So for me, I want to offer just a kind of a slight apology. My boss at B+H Architects, Douglas Birkinshaw, delivered a lecture, I guess very similar in content to this, about a couple of years ago here at the school. His focus was primarily cultural. I want to sort of divert the discussion and be, strictly speaking, a lot more technical. And again, this kind of ties back to this idea of these symposia helping all of us develop a technique in order to tackle the challenges that we face every day. So I have a lot of slides, and I'm really excited to be here, so please excuse the meter. I'm going to go really, really fast. There's lots of stuff to get through, only because I want to talk about lots of stuff. I have a personal relationship with one of these projects. I want to talk about a couple of case studies of how we look at cities in terms of their kind of renewal. And I don't want to talk about it in terms of maintenance, deferred maintenance or that type of thing. I want to talk about it in terms of optimizing and renewing and bringing the fabric of the city forward, but still maintaining, linkages to the iconography of the city as it develops. So the two projects I want to talk about, I should give a shout out to our clients and our partners. These projects are done in large teams, and we have very intensive collaboration. So Moa Dharmashanan out of New York are experts in recladding. Halsall, the sustainability engineers, helped actually develop the LEED EBOM certification rating system in Canada. Those two rating systems are going to be applied to these projects, and they both achieved LEED Gold. Intuitive were our structural engineers, TMP, mechanical, Dialogue, electrical, and Mark Brook from BVDA was our envelope engineer. So the two case studies are First Canadian Place Tower and the TD Centre, downtown Toronto, high-density commercial office towers. And just before I kind of launch into sort of the specifics, and they'll be quite specific and a little bit technical, but that's where I like to seat myself. The idea here is that for me there was a huge awakening or awakening. I don't want to be too poetic about it, but there's the pre-design phases of these projects became hugely extended because, as it turns out, renewing existing buildings is highly complex. And what I mean to say is that we brought all our engineers together, all our clients, all the operators of the buildings we brought together. And then we had this rational model of how we thought the building should operate, and we did digital simulations of what the energy consumption and water consumption would be. But then, of course, we tested it against what the operators understood the operation of the building to be. And, of course, the two, or not of course, but we discovered the two didn't really synchronize very, very well. So there was a huge kind of mining of the project designs and a mining of the project data that had to occur, talking to old associates of the firm, talking about the operators, digging up old drawings, understanding how the buildings were renovated, looking at utility data, and trying to put that all together and analyzing it multiple times in iterations to finally develop a rational model that matched an existing set of empirical data. We also used the LEED EBOM system as a tool to try and navigate that huge array of information. The EBOM system, as differentiated from new construction, maintains a recertification process. Once you're certified under the existing buildings operations and maintenance system, you have to recertify at minimum every 5 years. So, for example, on the energy performance side, you have to benchmark the performance of your building for a year, design systems that will improve that performance, predict the improvement of the performance, run the building for another year, and if you succeed, then you get certified. So it's actually quite rigorous, and then of course you have to recertify. So we used the LEED EBOM system as a guideline and a strategy in terms of how we metered and sub-metered the buildings and how we extracted all the information and did our energy auditing. And lastly, I want to say it was hugely exciting for me. We were really brought into the logistics of construction, more so than we typically get involved with, in that the designs that we needed to implement, of course, had to be accessible and operable from a construction point of view, otherwise the design was no longer feasible, and I'm going to get into that. So I want to start just with a couple of slides. This is a bit of an inscrutable slide, but this is an old heat exchanger in the basement of First Canadian Place, and it's like, this is what you run into. The engineers are pulling off valve covers and heat exchanger covers, and it's like nobody exactly knows where all the pipes are connected. And so you start this almost archaeology of diving into the project. We're looking at old drawings. This drawing was done by my technical mentor at B+H, a guy by the name of Bill Van Loon. He retired from B+H after 45 years. He was the original job captain on the project. I was the job captain on the First Canadian Place, so there was this kind of rich history there. And being able to sort of discuss with him how he drew up these extraordinary details was an amazing education. And then, of course, we talk about the logistics. I mean, we want to reclad this building. Well, we're talking about the rolling out of infrastructure level scale works. And dealing with that was a huge challenge and very, very exciting for me. So first case study, Toronto Dominion Centre, and I'm going to ask Jonathan, please help me keep on track. I'll kind of speed up if I can. Here, of course, we have a Toronto icon, an amazing modern building, and that it's achieved heritage status. So, of course, when we want to renew this building, this didn't color, but it filtered every move that was made as the renewal of this building unfolded. So, of course, we have this conception of these black monoliths, but of course, they're aging, they're turning gray. And we start to see that even though they're elegant and robust, all buildings require some tender loving care, and we had to start to analyze how we were going to repair and remediate, not remediate, but renew the building. So as it turns out, our initial simulations of energy consumption really started to look at the envelope. And of course, the envelope, single glazed windows on steel bar stock. That's about, in current standards, as bad as you can get. It's basically a thermal sink on the outside. So these exterior eye sections that, of course, create this incredible rhythm and elegant proportion to the building are really radiators of heat. So how are we going to deal with that? So first of all, we get rid of it, remove it kind of surgically. And then what we do is we design, in conjunction with Heritage Consulting, a new aluminum thermally broken window system. And this is a custom extrusion that will take a new insulated window unit. And of course, it was tinted single glazing previously. How do we create an insulated glazing unit now that doesn't completely rupture the kind of initial design, the initial your initial perception of that building? Because of course we're going to put in argon fill and warm edge spacers and a low E coating, which drastically affects the way in which you perceive that glass. So it took a long time to develop what that glazing would become. And here's the final installed version. We also looked at insulating that steel, and given the amount of embodied energy that we would need for the foam to insulate the window assembly, it was still a huge thermal bridge that in the end we decided that pumping all the foam in there wasn't really worth it. This kind of talks about the sequence of it. So this building, and when I get to the First Canadian Place, you'll see that there's a bit of a difference. This building really focused on the envelope as a means by which we could improve its thermal and energy performance. So there was an external swing stage system used. The windows were internally glazed so we could bring the units in from the inside, remove the old one, add the new insulated assembly. And because it had so much higher performance than the original assembly, you can see at the bottom, there's the old induction units, very powerful units to blow heat up on those windows to prevent condensation. Well, now that we have the higher performance insulated glazing, we have these very slim, much lower power induction units up in the ceiling. And of course, the net effect, we have this amazing increase in floor area. Coming back to my point about really dealing with the logistics, both these buildings had to be fully operational as the renovations were underway. So this was part of the design process, convincing the client, convincing the constructor about what the process would be of implementing the renovation. So of course we moved the furniture away after the occupants go home, and this happens all at night. The swing stage is dropped down to the right stage. On the inside, the unit is brought in place, installed, and then in the morning the furniture is replaced, and then business as usual. This shows the swing stage, and this shows the small induction unit that we could actually fit into the ceiling. There's the old induction unit, nearly 2 feet wide, nearly 2 feet deep. I'm sorry, I'm going to switch from the pointers. This one doesn't have a pointer, I apologize. And then here's the new installation. So the building becomes that much more usable. I should mention too that the building is black, and but of course, as architects, we understand that colors are highly, it's all about perception. And so it took us a year to pick the black that would go on the building. And of course, heritage. This is a huge deal. And one of the problems too is the original paint, which protected the steel which was a very good protector of the steel, had high lead content. Of course, we can't do that anymore. So we had to pick a paint that was durable, a paint that was less toxic, and had the right shade of black. And here it is. You can see the transformation of the color. Now, having said that, of course, this idea of heritage traced itself through all aspects of renovation. So there was a delicacy and an attention to preserving the elegance of the original building. Everybody was challenged and excited by this. So of course we wanted to put in LED lighting, but it had to be the right temperature, and we focused really. We wanted to maintain, a rich color spectrum in the light, and a lot of attention was paid to the lighting. Even elevators, as the old elevator, putting in LEDs, we had to be careful and kind of nestle them away and still try to maintain the elegance and of the original design. Here's the original lobby. We replaced the mosaic tile soffits, and of course, as we do that, the building has to be operational. So this is the kind of logistical installation. And again, we have to sort of design it. Here's above it, we're removing the ceilings, but of course, some of the tiles are lost. And this was of prime importance to the Heritage Board, that we had to replace that existing tile. How do we do it? Well, we actually took it down, washed it, and then reset it in new boards and put it up. And so the new tiles that we used were just a fraction of the old ones. And there's the new, the renovated lobby. Here it is kind of in process. We also replaced the waterproofing insulation of the plaza. Yeah, so they were getting rid of the, moving the, I mean, they graze for a long time, They don't seem to mind the winter, but, ripping up the existing plaza, putting down new waterproofing, and then new insulation. Again, it really is trying to bring it right back and being very precise about it. And these are a bit cheeky images, but ultimately we know what it's going to end up being. There it is. There's the new green roof for the banking pavilion. And then here it is. It's renewed. And this was the first building in Canada to get the EBOM gold certification, and that's one tower. And there's been 3 other towers in the works, and the next tower got LEED Platinum. So I want to now move. I have a very strong personal relationship with this project. I worked on it for about 5 years. And First Canadian Place, a bit of context, it was designed and built in the early 70s. Edward Durrell Stone was the American design architect with B+H Architects as the executive architect. I just want to point out that this gentleman here, Mr. Tono Altasar, is still a partner at the firm, and he was a senior designer on the project. So we have kind of this amazing resource to the past of this building. We start with, there was an unfortunate event. One of the panels was blown off in the wind. Nearly 10 years ago. The stone, it was a thin stone-clad building of Carrara marble, and the stone was deteriorating. And I think everybody knew that by looking at the building. It was just starting to show its age, but now it became a problem. And the building ownership immediately adopted a sort of a remediation strategy, taped all the panels together, and then, halftime? Okay, I think we're going to be okay. A strategy for taking this opportunity to renew the project. So now our analysis begins. Where do we start? Anyway, we kind of started with this sort of durability aspect of bringing the cladding up to speed, but we had to understand the mechanism of stone failure and its thermal or hygrothermal hysteresis. Just really briefly, because it was a cladding system, a range screen cladding system, both surfaces of the stone were exposed to various wetting and drying and thermal loads. And what tended to happen, because the stone Carrara marble is, in retrospect, probably not the right material for our climate to install, it's porous and it absorbed a lot of water, and then the outside would dry or the inside would dry at varying rates. And so the stone would deflect. And being stone, as it dried, it developed this memory, this history, this hysteresis. It would deflect, cup, and then it wouldn't deflect back. And over time, all these thousands of cycles, the stone started to deflect, and eventually one fell off. And we started doing wind studies of the building, and we discovered that you can see where the red here was the maximum pressure. That's actually where the stone was pulled off. We looked at historical records of the wind loading, or the wind tests, and of course all the new higher towers around this project increased the wind speeds dramatically. And so we had wind forces nearly double what was originally conceived. We also looked at how the sun was falling across the various faces of the building. We did extensive energy modeling to understand and to try to develop a model that was precise enough so that we could make predictions on how our new systems would affect the end outcome. What we discovered about this project separately and uniquely from the TD Center was that this building already had actually a very, very good envelope. It was a rain screen stone with 4 inches of insulation and a very controlled window-to-wall ratio. And one thing we should note about this building, it's 30,000 square feet per floor and 72 floors of it. So the actual perimeter zone effect on the total energy consumption of the floor plate was actually quite marginal. So we did studies about adding insulation, more insulation to the exterior. We started to get very diminishing returns on our energy performance because it had that sort of inverse relationship to the energy performance that the TD Center had. So the focus of this renewal became the innards. It became the mechanical systems. We started really diving into how the interior of the building operated in order to bring up that energy performance. So I just want to talk a little bit about the recladding. So the recladding then became really an exercise in durability. How are we going to put up a lasting, new, fresh, innovative new cladding system? So there's a whole bunch of design options that we considered. We considered stone, precast metal, even microcrystalline, which is maybe a bit newer. We looked at colors and we looked at do we cap the building or not cap the building. One thing is we discovered we love this sort of hat, if you want to call it, but First Canadian Place generates a huge amount of revenue by the radio towers on the top. And a lot of the emergency dispatch in Toronto is actually dispatched from those radio towers. So any of these screens that we put up interfered too heavily with the radio dispatch. So we had to abandon that. Here's the kind of the image of the thing. Here's the old kind of array of panels, stone panels. And here is the new proposal. We're proposing basically 8 feet by 10 feet of glass, unitized glass spandrel panel. And that was, again, talking about how the logistics works. I want to talk about how the construction platform worked. We had to actually measure the capacity of the construction platform against the weight of these panels to see if they jived, to actually understand whether this design was feasible. And we did that, and I'll show you that a little bit later. So we ended up kind of finalizing on glass. You know, glass is just an amazing material and has kind of this sort of super sharp surface to it, but it obviously has very kind of mystical effects as well, and we wanted to play a little bit with that. So we looked at frit design and the type of and the color of the glass. Is it low mineral iron? Does it have a tint? What type of white? Just an extensive kind of array and a lot of fun and just really. Oh, sorry. Sorry about that. I wanted to explain that slide first. So we did go to the glass plant. All the panels were triple laminated tempered glass. So we did a lot of research into the glass technology, and this was at Agnora's glass plant in and around kind of Barrie, where we were looking at the size of light, and not all shops can temper correctly the size of lights we needed. And what this shows is that there's a lot of effect here, but when we temper the glass, we're obviously building in a lot of force. We're pre-stressing the glass, and that's what gives it that strength. But when we release that force, the tempering, collapses the glass into teeny little bits, and that's why we call it safety glass. So what we want to do is when we actually do rupture the glass, we want to test the consistency of the pebbles and the array of force distribution across the glass. And so this is what this test is doing, but it's more to really show us that there's all that force locked in here. You can see this one guy who was chatting away to us, a salesman, and he forgot that he wasn't paying attention. He nearly fell over on that 2x4 holding the edge. So, I mean, that was a lot of fun. Also, so we also did a whole bunch of studies on if we're going to frit this triple laminated assembly, we have this opportunity to give it a bit of depth and play with maybe moiré patterns. Ultimately, I think we didn't really pursue any of these. Again, it was so much fun just kind of going through it. But tying back to my intro about there's kind of an archaeology of a project that we initiated, we went back and started looking at Edward Earl Stone and what fascinated him, and he was very interested in this sort of this triangular geometry, and so we actually tried to kind of maybe call upon that a little bit or invest a bit of energy in that. So this is just one of the videos we made for the client showing some of the inspiration. We ended up kind of choosing this triangular pattern as a frit pattern for for the glass. Maybe I can show you. I don't know. Yeah, there you go. So there's the very simple geometry. But that's on. So it's triple laminated. So we had two interlayers in there. So the outer interlayer has this pattern, and the inner interlayer was opaque white. And so there's a little bit of depth there. The light kind of plays across that assembly in a kind of delicate way. And this just shows how it's all going together. It's all pre-glazed. It's manufactured in the factory and then brought to site unitized. And this shows the process. We remove the old stone. We remove the old insulation. There's clips that hold the old stone. We remove those. We remediate and repair any of the spandrel steel. Put on new anchors, new insulation, and then the new glass panels, and then the final trims. So that was the design. In parallel, we're working on a system to try and implement that design. We call it just generally the logistics. So we looked at mass climbers, swing stages. You might remember for TD Center we used the swing stage, but here we didn't use either of those. We used a custom unit. They ended up calling it the suspended elevating platform. This is a rendering we did, and it's a 3-level system. And maybe I'll get the pointer here. So on the bottom, I have to point it in the right direction. On the bottom is where we do all the demolition and removal of work. In the middle is one of the things that makes this unit quite special. This whole apparatus is suspended via cables to winches on the roof. And that's what allows it to move down the building. But then when it's at the right level, it's locked into place. They weld on studs onto the steel, and we attach custom hangers, and this unit bolts right into the building, so it's extremely stable. So we had the capacity to lift these glass panels. And then at the top, so the middle layer was the attachment layer to the building itself, and at the top we had a monorail, and then we just sort of slide the glass into place on the upper level. So this shows you in section what we're doing. So at the bottom, the stone is removed. Here is where it's tied into the building and makes this thing a very, very stable logistical platform. And then here's the top with the monorail and when we install the glass. So, we were involved in this, and this is not sort of typical, and it was a huge learning experience, and again, very, very exciting for me. This shows more of a design drawing. This shows the fabrication drawing of the platform. I mean, I've been accused of being a geek, but I love this kind of stuff. I think this is fantastic. So here's the system working in place. This is just trying to give a kind of overview.
The recladding of First Canadian Place consists of 8 independent access platforms positioned around the circumference of the building. Starting at the top and working in a corkscrew-like fashion down the face of the tower, separate teams are responsible for removal, remediation, and replacement. In the first step, the old marble is taken off and moved off-site for recycling. Next, the original fixtures that held the marble are removed, the remaining surface cleaned, and new insulation and fixtures installed. Last, the new glass spandrel is attached. One 8-foot by 10-foot glass panel replaces 8 pieces of marble. The existing windows remain in place. Each laminated glass spandrel consists of 5 layers fused together, 3 pieces of glass and 2 pieces of laminating substrate material. A white ceramic pattern, known as a frit, is printed and fired as a geometric design within the assembly. The frit is styled to create...
Okay, so that gives you kind of an overview of the process. Now I just want to run through, this project was also a huge challenge for me because I'm afraid of heights, so going up 72 stories on this platform was a real personal challenge, and I'm glad I made it. So these are photos of the process. So we take this, what they call man and material hoist up to the appropriate level, and then we get off and we enter the suspended elevating platform. We start removing the stone. We found this amazing panel here. This is a kind of a Latin translation. The stone from Italy, obtained from the patrician father A.B. Ottoni, is drenched with sweat and tears. So we found this kind of poetic stone on, I think it was the 27th floor or something like that. So that was actually, there was 2 of them, one on each side, and one of those stones was sent by Brookfield back to the family in Italy, in Carrara. So we're removing the stone. There's the old insulation. Given that this is 40-some years old, that insulation is in pretty good shape. This was early rain screen technology when it was drawn up. So the performance was proven. Cleaning up the insulation, putting on new anchors, putting on new insulation. This is fire-rated insulation, 5 inches of mineral wool. These are the studs that are welded on that carry the that will carry the custom anchors that lock the system in place and make it quite unique and make it very, very durable. There's the new anchors. We're taping it. We're also, if there are any kind of cracks or holes, we're replacing that. And here's the new glass, and this is how it was installed.
Oh yeah, you've been figuring out the radius to make that.
Yeah, no, but exactly. See how tight it is?
Oh.
Yeah.
Let's stop you.
Don't really need the audio, but anyway. So then here's the new glass panels being installed. That's Mark Brook, our envelope engineer, really smart guy. And you can see the effect of the light across that glass, and it does change. The light really has an effect on it. I became quite enamored with it as the project unfolded. And this is just a series of images that I may kind of talking about. The thing also has a presence in the city. So for 4 years, this thing, you'd watch these television shows in Toronto, and you'd see this donut in different places, depending when it was when the show was filmed. Also, now I just want to finish up with that was the cladding. That's kind of the sexy part. But the building had this intense regimen of internal renewal. So there was 2 aspects to that: actually taking the systems and putting in new high-efficiency systems, but also there's an idea of studying what was there and how those things were tuned and retuned and retro-commissioned and how they were sub-metered, and new controls were put on there so that whatever systems were in place could be operated at a higher level of efficiency. So one of the big things that we discovered was that the original design for the mechanical system actually wasn't installed. The original design had heat recovery chillers. So a typical building has a chiller, takes the heat out of the building, sends it to a heat rejection device, a cooling tower, and that's how the process goes, and consumes electricity in order to power that chiller. What we do here is the chillers remove the heat from the building, but the building ventilation system is an induction system. It requires a primary heat source. So what we're doing is we're taking that heat out, instead of sending it directly to the cooling towers, we're putting it into a primary thermal loop. So already we're increasing the efficiency there. We put in all condensing boilers, 90 plus efficiency. We put all the ventilation was demand control. So we put CO2 sensors on all the return air decks so that we only ramp up the ventilation as we occupy the building. We looked at everything, including washroom exhaust. We put a scavenger heat recovery on the washroom exhaust. The perimeter induction system that I talked about that requires that primary heat, we turned all the motors to direct drive motors so that they could be ramped up and down and have they're not just on and off. Everything had control. We put variable speed drives on all the drives. And this is a very, very unique one here, demand response charge reduction. Because this building is such a big client for Ontario Power Generation, they developed an agreement that when we approach peak periods, they get a call. Brookfield gets a call and they say, we're running out of electricity here, can you turn off your chillers? So they turn off the chillers for 3 hours and they get a rebate from the utility. So, this is where we can start talking about how individual buildings are not, as individual buildings, are not really the solution. We need to start developing broader urban networks that start to manage our demand and share energy. And this is kind of the first step. I found this very interesting. And this kind of came out of this whole sort of lead EBOM study. And then we did retro commissioning. I just want to indicate, there's a whole regimen of stuff that we did on the interior of the building, including, saving water. Now, one last kind of, I think, really important thing that we discovered. When we put in the heat recovery chillers, we're saving the operation of the cooling towers. And there's 2 huge cooling towers at the top of the building. They use a lot of water. And because they're so high volume, there's a percentage lost in evaporation. Running those, saving the operation of those cooling towers, because we installed the heat recovery chillers, the savings in water evaporation for those cooling towers in 3 years paid for all the new chillers. That's how much water is pumped through this system. So, and we're just talking about, the water, it's potable water they use, so you're charged a rate from the city. So the savings over 3 years by not running those cooling towers to the extent they were paid for, like $1 million worth of chillers. So I found that pretty amazing. That's the kind of scale of the building. So, and then of course there's always the challenge. You have to retain your tenants. You can't just renovate your building and then the tenants get upset and they leave. So it was rolled out in these particular phases. And then here we're just tracking some of the energy consumption. And one of the kind of challenges is as these systems are put in place, nobody really knows how to operate them or balance them yet. It usually takes several months or sometimes years for the curves. The blue line is our baseline curve moving from summer to winter. And then you can see in 2009, all the new chillers are thrown on and they're not quite balanced. And of course, there's a spike in energy consumption. But we're getting down now to, well, we have data now beyond this, but 2011 now we're starting to kind of creep just below our baseline. So it's now LEED EBOM Gold certified. And I want to thank you very, very much. I know that was, I think that was probably a little too fast, yeah? So, but I really appreciate it. Thank you kindly.
Wow, thank you so much, Kevin. That was incredibly dense and really fascinating. We do have time for a couple of questions. Michael.
This is a great presentation. There's a phenomena of towers leaving their lights on. And there's a mythology about why that is or isn't so. It's got to be a source of a huge energy consumption.
Absolutely.
And of course, night sky pollution.
Yep. And you're right, that's a huge challenge.
How is it true that they can't turn them off? And if so, what can be done to make that possible?
Okay, and I think that's a real challenge, actually. So turn off the lights. How hard can it be? Well, there's agreements with tenants about what lights should be left on, what hours that they operate and they don't operate. And with buildings of this vintage, nobody cared about turning off the lights. So actually the controls weren't even there. So the tenant agreements were in place on the way that the system operated. Changing that actually became not politically, but sort of the politics of the economics became difficult. On the TD Center, they were very smart. Cadillac Fairview developed a tenant engagement process where they involved them in the ultimate energy savings, and so it became very easy at that point to renew the leases and draw them into a relationship where there's a dashboard where they can see how much energy they consume and why, and it's very transparent. And they can also see, and this is a very important point that Jonathan and I were talking about earlier. Tenants, they want to obviously know how much they consume. They want to pay for it per kilowatt. But until you tell a tenant how much they consume relative to the average, change doesn't occur. So when you tell them, oh, you're 10% over the average, whoa, we better do something. Everybody wants to be 10% below the average. And so that kind of forces the change. It's the benchmarking that's important. So as part of that process, they develop a benchmark for the building. And of course, you get rebates and incentives if you push it down. So that's how they did it. Here at First Canadian Place, it was really an issue of controls, putting in the proper controls, selecting the right light. 72 floors, everybody had to agree on the right kind of ballast and the right type of system. And were you going to use LEDs or were you going to use dimmable fluorescents? So there was more of a controls issue. But you're right. It was the lights were left on because there were agreements in place, and it was easier to do it that way. And now it makes a big difference when we put it into the LEED system. Changing the lights, there was a huge credit on the energy saving side, so it became easier to do that. Thanks for that.